Sairam and welcome to the next session in Big Data Analytics. Let us start this session with a prayer. Om Sai Ishwaraya Vidmahe Satyadevaya Dhimahi Tanna Sarva Prachodayat. Om Shanti Shanti Shanti. So let us quickly review what we discussed in the last session. We looked at what is big data, and we understood that there is no formal definition, but our intuitive understanding is that the volume of data is so large that it does not fit into memory. So remember this point always, that amount of data is greater than the available memory. We also saw where big data scenario is available and applicable, and in the current day scenario we understand that in most of the situations which we commonly use in our regular life, big data analytics is quite applicable. And because of that, we find that it is quite a relevant area to study, and the reason is that it can generate business value. It can generate business value, and that is why this course is many times preferred. We also saw the other definition given for big data with the 5 different V's. Let me quickly recapitulate all of them. Volume, we understand that the volume of data is quite high. Then we have variety of data. When we say variety, we understand that there are 3 different kinds of data that we saw. We can say is unstructured, semi-structured or structured. Then we were looking at the velocity of arrival of data. The rate of arrival of data can be quite high, so we looked at velocity. Then we also talked about what is called as veracity, where we are talking about the authenticity of the data. Authenticity, this data should be real and it should not have bogus numbers. And finally, all this is useful only if we are able to do some analytics and bring up some value. And when we say value, of course we are talking about business value. It could mean concern to the problem that we are solving. We should be able to bring some value. So these 5 V's also are characteristic of big data. Apart from this, we also attempted to look at big data algorithms, and when we looked at big data algorithms, there are 3 specific features that we were talking. One is that the input data is quite large, which again means that this is greater than the available physical memory. And with respect to output, we said we are not that much worried about accuracy, but can we bring up something like approximate? And we also defined approximate, saying it must be good most of the time. Good most of the time. And last, with respect to computation, we said that we need not follow the traditional model of computation where data is fetched according to the CPU execution. But in this scenario, we are going to say move program to the data. Typically, we always find that data moves to where the program is available, but here we said it should be move program to data. And there is also one more point we discussed here. We are saying that this feature is going to be applicable using the looking at the complete picture of multiple nodes. We are any day talking about multiple nodes. Remember that the scenario does not change within a single node. So that summarizes our previous session. So let us move ahead into the next part. Now, the big data problem When I say big data problem, we are talking about processing very large amounts of data. We want to talk about processing large amount of data. Now, this is not a new problem. In fact, the scientific community is well aware of multiple solutions to this problem, and you will find that there are a lot of solutions that are available in this arena called as high performance computing. The typical solutions have been either to generate really large supercomputers, so I can say large mainframes. We might have heard of this term called mainframes. Or there are also solutions where they talk about using a cluster of machines. Now, there are both solutions available in the HPC area. But one fact that we must observe is that whether it is the large mainframes, definitely it is going to be specialized hardware and specialized software that is required in order to run your application in large mainframes. Or when you move to the cluster, at least you may find that either the machine's CPU or the interconnectivity, one of these things or multiple combinations of these are specialized. And therefore, in terms of economy, both are expensive. Now, this was something that the big data area wanted to avoid. They did not want to go for an expensive solution, and therefore they wanted to bring this to a common man where any vendor is able to run a big data algorithm, and therefore they came up with a commodity solution, and the solution is called as a commodity cluster, which means that it is going to be similar to what we are looking at. It's a cluster of machines. But what is so special about, in fact, I think I should not use the term special. What is so common about this commodity cluster is that we can build this commodity cluster just out of simple desktop computers that we regularly use in our daily life. And the interconnectivity can be very common, like how we use Ethernet. Now, that's a commodity cluster. In fact, what we use in our campus, what you all work in your computer lab, if we are able to install a few software packages, then we have almost set up a commodity cluster, right? So we have normal desktop machines, and we are using a very common interconnect called Ethernet. Of course, the prescribed is that at least there should be a 1 GB Ethernet, and in our lab we have an Ethernet which is much better than this. But for a commodity cluster, this is the requirement, so which makes it extremely inexpensive. So that is the idea behind coming up with a commodity cluster. Now, the moment we come up with the commodity cluster, instead of specialized hardware, which is expensive of course, it also brings added problems, and one of the most important problem that comes along when we try to use a commodity cluster is reliability. This becomes extremely tough in when we go for a commodity cluster. And what do I mean by reliability? Now, a common scenario could be like, when we work in the campus, we find that there are lab machines that simply crash once in a while, or you may find that the hard disk may fail at one point of time, and there may be even harder problems where we may have a motherboard or a CPU failure. and therefore it is not enough if we are able to come up only with an inexpensive solution, but can we add reliability to it, and therefore can we combine these two and bring up this solution, and that is what we are going to look at. And so the solution comes as two pieces of software. One is called a distributed file system, and the other we are going to look at is a distributed computing platform. We have so what is the hardware? The hardware is a simple desktop cluster connected by common interconnect like say Ethernet, 1 GB Ethernet. And what do we have in the software? It's a new software stack we are looking at. We must have a distributed file system and we must have a distributed computing platform. So let us try and understand each of these one by one. And before we get into each one of this, let us look at the hardware. How would the structure of the hardware look like? And that will be helpful for us to understand these two in the software package as well. Now, how is the hardware organized? Hardware is organized into computing nodes that are assembled in racks. So we have computing nodes and the next unit is racks. So we combine 8 to 64 nodes in a rack. So it's up to us to dependent on the capacity of the rack, we can fit either 8 or till 64. I mean, that's just a definition. There is nothing formal about it. So we can arrange 8 to 64, and if you want to have an idea of a rack, you can remember the rack that we used to have in our campus inside the server room, where we can imagine that, let's say, systems are arranged in the horizontal order, right? So we just take systems and we fix them into the rack horizontally. Now, very important fact about the rack is that all these systems that we are going to fix into the rack are going to get interconnected by a switch. Now, when we say this is a network switch, and as we mentioned earlier, we are using a gigabit switch. When I say gigabit switch, the bandwidth is 1 gigabits per second, not 1 gigabyte but 1 gigabits per second. Now all these nodes that are there in the rack are connected by a interconnect switch, and this is obviously, it should be called as a intra-rack switch. Similarly, you replicate this unit of organization of a rack. Let's replicate it to say now we can call this rack 1. Now we can get rack 2, rack 3, etc. Now I have not drawn the intra-rack connectivity for rack 2 and rack 3. I have not drawn, but the point is that we need to assume that all these nodes are interconnected. They are connected within the rack. Here also they are connected within the rack. Now if you want to connect all the racks together, then we use another switch or a hierarchy of switches. So it need not be just one switch, it could be a hierarchy of switches, multiple switches connected in a pattern, and we call these as inter-rack switches. They are inter-rack switches because they connect racks to racks, not from node to node, but they connect from racks to rack. Okay. And typically the bandwidth here for connecting inter-racks is generally greater than the bandwidth that we have here in the intra-rack. Now why is that so? Because here you just you are connecting 8 to 64 nodes in a rack, within a rack, to a network switch here, whereas when you are talking about the inter-rack, you can try and imagine the number of combinations of the nodes that can happen. So if you are talking about say node 1 to 64 here, if we talk about node 65 onwards to other nodes here, etc., you can imagine the number of combinations of parallel connections that may be needed across the racks, and therefore this bandwidth any day is kept a little higher compared to the bandwidth that we are choosing for the intra-rack switches. As we mentioned earlier, we must remember that these are simple nodes. When we say nodes, they are just like some normal desktop systems. There is nothing special about these computers. And the switches that we use are also like commodity and regularly available switches, which means we said that it can bring in this problem of reliability. Now, with specific to this kind of hardware organization, what would reliability mean here? We could mean loss of a node. No, like in our lab, we say that, sir, one particular system has failed. So similarly, a specific node could fail. Second is, what if this can happen? Loss of a rack. That's a more serious problem. And why is it that we are writing loss of a rack? Because probably we feel that the rack can be lost only when all the nodes in that rack can be lost. No, but there is one very important factor that we have to look at, and that is the intra-rack switch. Imagine if one of the intra-rack switches fails, then we have lost the entire rack because we don't have any connectivity to that. So we have to assume that these problems are possible and come up with a good solution. And what is the typical solution that we are going to see? The solution that we are going to see is replication. In order to solve the problem of reliability, we are going to use the solution called replication. What do you mean replication? If we take a file, we are going to keep multiple copies of the file on different nodes. So if a specific node fails, we may find its copy somewhere else. Okay. Now we are also talking about loss of a rack. Then what do we do? When we keep multiple copies of a specific file, we must not keep them in the nodes within a rack. Rather, we should be keeping those copies across the racks. Now, why is it that a better idea than keeping within a rack? Because we are also discussing the issue of how to handle loss of a rack. Therefore, it would make sense, instead of storing a file, if the copy of the files, instead of storing it within a rack, let us try to store it across multiple racks. Okay, but storage is not the only issue. We also have to speak about the solution not only in terms of storage, but what about compute? Even in compute, I am going to say that replication is the solution. Why? Because we are going to run tasks across multiple nodes and multiple racks. And what if a specific task, or in fact all the tasks, we use a framework such that they are replicable tasks. So moment we are able to identify that a specific task has failed, what we should be able to do is to replicate or create a copy of that specific task, and it should not affect other tasks that are already progressing. So keeping these two ideas in mind, the solution idea is simple. It is one word answer, replication, but we are going to apply it to storage. We are going to apply it to storage, and we are going to apply it to compute as well, and we have to come up with a good solution in the software stack. And that is the solution that we are going to discuss in two levels. One is the distributed file system, which is going to help us in replication at storage level, The second is we are going to discuss about distributed computing platform, where we are going to get help on replicable tasks. So let us now, given this understanding of the hardware and the problem and the solution, proceed into understanding each of these components in this new software stack. Let's begin with the distributed file system. There are many examples of distributed file systems that are available. For example, we can talk about the Google file system. Then we are going to see HDFS. HDFS stands for Hadoop Distributed File System, and there are many other such examples of distributed file systems that are available. What we are going to look at now is the most common feature of how a file system stores files, and as we discussed earlier, how does it help in replication or redundancy. The first aspect of any distributed file system is that they will divide files into chunks. Chunks are nothing but equal sized parts of files. So if I have a file, let's say a.txt, which is of size 2 KB, I have to see what is my chunk size in order to identify how many chunks this will produce. So the chunk size is very dependent. In HDFS, one simple configuration in HDFS is that chunk sizes can be set as 64 MB. When we say 64 MB, let me just try to convert it into 2 powers so that it will be easy for our calculation. That is 2 power 20 per mega into 64 is 2 power 6, so that means 2 power 26 bytes. This is the size of one chunk. So when we look at 2 KB, obviously it is fitting into one chunk, and therefore this is simply divided into a single chunk. Now what about 128 MB? I have a b.jpg which is 128 MB. So it's clear that it is going to divide this into 2 chunks. Suppose I have a file that is 1 GB size, then what would be my number of chunks? So calculating this will be 2 power 30 divided by 2 power 26, that is 2 power 4. That means I would be able to get 16 chunks. Okay. Now the first aspect of any distributed file system is to divide files into chunks. Now, we may ask a question: what if the file size is not a multiple of the chunk size? Then we can say that the remainder or the last chunk may not be exactly 64 MB. Either the remaining part could be filled up, or there are aspects where it can be left out. But typically any file system, any distributed file system divides it only always into equal sized chunks. Now after dividing them into chunks, these chunks are now replicated across in the nodes and across the rack. Let's take an example. Let's say that we have the file a.txt. Now that the color should help us to understand where these chunks are getting placed. Now we know that file a.txt has got divided into only one chunk. So let us see here. Yeah, so we see that there is A1 here, indicating that this first chunk of A is here in rack 1 in node 1, node 2 in rack 1 we have got A1. In rack 2, 1, 2, 3, 4, node 4 has got A1 again. Similarly in rack 3, node 1, 2, 3. So rack 3, node 3 has got A1 again. Now remember, we wanted to replicate, and in fact I have replicated not just once, twice, but thrice. So that is again dependent. It's a parameter that we can set in any distributed file system, that's called as replication factor. And in this example, and typically in HDFS I can remember stands for Hadoop Distributed File System, replication factor is set to 3. its chunk size is 64 MB and its replication factor is set to 3. Obviously these parameters can be changed, but since these are the common parameters, I am taking an example working with the same parameters. Now let's move to file b.jpg. We have got two chunks. Let's see where they are located. I have b1 here in one node 1, 2, 3, 4 of rack 1. Similarly here in rack 2 and here in rack 3. Then b is not only having one chunk but has got two chunks. So look out for b2. Yeah, b2 is here and here and here. Now if you look at C, I mean there are 16 chunks, but I don't think we need to mark out everything. I think you got the idea. So if you look out for the initial chunks, I have marked out C1, C2 and C3 across different nodes on the on different nodes and on different racks. Great, this solution is good because let us say that I'm reading a.text. So I have picked up this chunk A1 from node 2 on rack 1. Great. Now as we are reading this file, or as we are using this file, let's assume that somewhere this node fails. What will happen now? Since this node has failed, we now need to take a copy of this from some other rack where this is being stored. So we could go to node 4 of rack 2 and pick it up from there, or we could go to node 3 of rack 3 and pick it up from there. Now similarly for any other file, so it is quite simple solution. It's quite a simple solution because we have simply replicated not the file but the chunks of them, and even if that one part is missing or if a node that is having it fails, then we can simply go to another node where a copy is maintained and pick it up from there. Okay. Now we understand that if this fails, we can go here and pick up A1 from node 4 of rack 2. But how do we know that? So the question, in order to bring solution of replication, we got this idea of distributed file system, good. But how to know where the replicas are maintained? That comes as a feature in distributed file system called the name node. There are other file systems where they also call it the master node. But in HDFS, this is maintained in name node. Now what do I understand by name node? Now all of us understand what is a traditional file system on a single node. If I have a single node and ask what is a traditional file system, we know that it maintains a hierarchy of the entire file system tree. Like I can have initially slash, maybe I have etc here, then I will be having bin here, etc. Now this is being maintained by the file system. The traditional file system is maintaining this. Now what happens in a distributed file system is that in DFS a similar structure is being maintained of the entire hierarchy of files and folders, but instead of marking what are the inodes, etc., which is maintained by traditional file system, instead of that, for each folder they store the node, the rack and any other details if necessary. So it is a idea that has come out from the traditional file system, but the distributed file system maintains for every file and folder where is it located, which rack is it located, what is the node where it is located. Of course I am giving you a very brief picture, but there may be many other details that can be recorded here in this structure. So how do I know where the replicas are? I consult the name node. In fact, not just for the replica, even if I want to know what is the location of a file, every single access to a file on a distributed file system has to go through a name node. Now how it works in HDFS is that the first access is to a name node. it is like a metadata lookup. So let us say that I want to access /etc/bin, then it comes to the name node, traverses the hierarchy, finds out for this particular folder where it is located, and it gives me the exact it gives me this specific location. After that, my program can directly contact that specific node, which technically we call as a data node. Okay, we need not worry too much about these specific details to HDFS. These should be handled probably in the Hadoop course, which is a separate course that we have. But since we are discussing distributed file system and we are going to pick up HDFS, that is why I introduced this term called data node. Otherwise, the idea is quite simple. When I want to access a file, I contact the name node. The name node looks up where this specific folder or the file is located. It gives me the rack and node. Once I have the rack and node, I can directly contact the data node and pick up that file. There are many more issues that do come in there, but we are not going to discuss this because it is not in the scope of this specific course. Now that brings up one more problem. What if name node fails? That's almost like the entire distributed file system failing, because we may have all the data available with us, but if the name node has gone down, then this entire metadata is gone. Once there is no metadata, I simply have data which we can't really read or understand, and therefore it's the loss of the entire DFS. So what is the solution? Typical solution that they use is replicate the name node, and they call it the secondary name node. Now, obvious question that's going to rise is, what if the secondary name node also fails? Okay, here let me give you a scenario. Let's say that name node fails. HDFS has a mechanism where once the name node fails, it will immediately bring up the secondary name node, but it will take quite an amount of time for it to come up, and once it comes back online, you will find that things will start working as usual. But what if secondary name node fails? We may have to replicate this further. I mean, there is no other solution in HDFS to say that, when both fail, what happens. So either at configuration time, you could say that I would like to have another secondary node. So you may have another secondary name node that could run, and if this fails, that would take over. So typically nobody goes more than a single name node with one replication with the secondary name node, and this is typically given to be a very good practical solution, and therefore we would stick to this kind of a solution. Okay, so two important points before we close this session. We see this file called a.txt. It is just 2 KB, and the minimum chunk size itself is 64 MB, which means that for storing a file like a.txt, using a DFS is a huge overkill. So we must understand that if we are going for DFS, obviously we are looking at large files or very large file size. That's what we are intending by saying large files. The second aspect is not many writes. It's a very important aspect when we go for DFS, that too specific to HDFS. Now imagine if we pick up, say, a chunk C3, we are reading a specific part of that file and we start writing to it. Imagine the work of the distributed file system. It must ensure that the copy is also getting updated, not in the first place, in the second place and third place, depending on the replication factor. And now that will also involve a lot of connectivity, the network bandwidth, and therefore keeping all the copies updated itself is a huge task. And therefore our assumption throughout this usage of HDFS is that we are going to use it in the scenario of very large files, and we really do not have many writes. We are only going to have a lot of read access, and that does not cause any problem. So I am hoping that we have got a decent idea about distributed file systems. Let us talk about the distributed computing platform in the next session. Let us close this session with a prayer. Om Shanti Shanti Shanti.